Hi friends, today I am going to start a new lecture series on electrical machines 1. So this is the first lecture on electrical machines 1, which is named as fundamentals of electromagnetics. So basically electrical machines are energy conversion devices, so which converts electrical energy to mechanical energy and vice versa. So this happens through the magnetic fields in most of the electrical machines. So we should know fundamentals of electromagnetics before getting into the electrical machines. So that's why in this lecture I'm going to give some brief terminology which uses in the electromagnetic fields and sources of electromagnets. So first thing we should know about what is the source of magnetic fields. So first one is there are two sources, one is permanent magnets and another one is electromagnets. So in permanent magnets case, so these are mainly from the earth, these are mainly rare earth magnets, so which is of neodymium and cobalt, so monosodium cobalt, which normally we used to play in our childhoods. So we have seen in our plus 2 and before SSC, like bar magnets and U-shaped magnets and ring magnets. Most of us might be playing with these magnets, which are commonly available in the speakers. So we might have played, one of us played with these magnets. So these are mainly permanent magnets. So but in this case what happens is, whatever the size of magnets we have and the material used in the magnets will defines the magnetic field that emits from this magnet, and the strength, basically we call it as the strength of the magnet. So whereas in electromagnets, so what we have is, we have a one iron bar which is shown here, iron bar over which the electrical current means conductor is wounded like this as a coil. So when current passes through this coil, the magnetic field will be created around each conductor, and which makes a complete magnet which forms north and south poles. Like here you can see that this is forming north pole and this is forming south pole, like the lines are leaving from north pole and coming to the south pole. Okay, so these are electromagnets. So where we can control our current passing through these conductors, and we can control the amount of magnetic field that can be generated. So here the advantage is that the magnetic field can be controllable. So how these electromagnets are created? First we should know how the magnetic field will look like in a current carrying conductor. So for that we will take a 1 ampere's thumb rule, right hand thumb rule, like not thumb rule simply. So we have to hold the conductor in a current by placing thumb in the current direction, and the remaining fingers of the hand will represent the magnetic field direction, like this. Suppose if I am holding my conductor in this, which carrying the current in this direction, with representing the thumb in the same direction, though my magnetic field will be in this direction, right, like this. So this is a basic principle. So from this we are going to use some convention now for the current directions. Suppose if the current is passing upwards, like this, like into the from the paper towards you, like, then it will be taken as a dot, and it is going away from you or from us, or like into the plane, then it will be represented as cross. How this came actually? So when you look at an arrow, so if you look at from this front view, like from the front of the arrow, you can see only this tip of the arrow, right? Only this tip, which looks like one dot around one circle because of this backside base. So whereas if you're looking from the tail point of view, then we have this type of structure, right? Every arrow like this, right? So this will look like a one cross around a circle. So if the arrow is going into the plane, then it will be cross. If it is coming out of the plane, then it will be dot. So if normally in normal case everyone will consider this is a positive direction of the current and this is a negative direction of the current. So here we have a dot, right? So that means we have to hold the thumb, right hand, such that the thumb is representing towards you. Okay, then the magnetic field direction will be in the counterclockwise direction, right? So whereas if the current is moving away from you, that is cross, then the magnetic field direction will be clockwise direction. Fine. So if we are applying this concept to a different number of conductors placed around an iron bar, like as a coil wounded like this, then when the current flowing from this side, then it will enter into the paper here, right? So it will be cross. When it is coming, and after that the current will flow through the back side of the conductor and come out of the paper here, right? So that's why it is dot here. Similarly here it is a cross and here it is a dot. Like that we have marked all the current directions. Then once you mark the current directions, the field of magnetic field here, it will be clockwise, as it is a cross, and it is here, it is a, what is this, counterclockwise, right? Similarly we have a clockwise here. So if you see adjacent coils, means like adjacent turns, so it will be counterclockwise here, clockwise here, and it is a and counterclockwise. So what will happen here, these two will form a loop like this, because here the magnetic field will be cancelled out because of opposite direction. Similar thing will happen here and here and here. So similar thing will happen here and here and here as well. So the complete magnetic field will be looks like a one loop like this. So which forms a north pole here and south pole here, right? So this is how an electromagnet will be developed. So these electromagnets will be used in the most of the mission, and even though yes, there are some permanent magnet missions which are nowadays they are getting the more popularity. We will discuss that one in the last of the lectures. So most of the missions, conventional missions which have been used from the long time, is the electromagnetic based missions. Okay, so next we will move to the we'll move to some results. So if you want to visualize these effects like counterclockwise and clockwise and all these things, there are some simulation softwares like FEMM, so which is an open source software. You can get the link for this FEMM software. You can download it and you can do this simple experiment like simulations to visualize the field. So here what I did, I took two conductors. One is this conductor, first conductor, and this is a second conductor. Okay, so here I have given the current in positive direction, like which is coming out of the plane, and here I have given the negative current which is going into the plane. So I have simulated these two to show how the magnetic field will be represented, and I plotted the H, means flux field intensity, so which is given the direction of the magnetic fields. Okay, this is how it will look like. So even you can try this type of simulations to visualize the magnetic field. So I will be using this software for the lectures as well, to give feel that instead of because most of the students will have the problem with visualizing the fields and other things. So here we don't have the such problems, so we can see these things in the FEMM software, so that we can get the better visualization or better understanding. So similarly I have done the solenoid like electromagnet as well. This is only two conductors, where I am showing the field generated by two conductors. So similarly I have done the same FEM simulation for the one electromagnet, where I have taken on M90 material, which is a soft magnetic material, so which is having good magnetic material property, and over that I have wounded 4 turns of coil. So here I consider the positive, and this is negative, this is dot, and this is cross. So I have plotted the magnetic field around this. So the number of lines will be probably like this, and we can observe this, there is no there's no lines here, right? As I said in last slides, here there is no lines exist here. So So whenever you are drawing some electromagnet, you should be careful that there are lines which goes like this, or you can see some of the lines is crossing here itself, not completely from the outside of this edge, right? Some of the lines is crossing this edge also, because it depends upon the length of the line which is going around. So in the magnetic lines, when we are studying the magnetic line properties, we will get to know why it is crossing like this, because the main reason is that the magnetic field always looks at the low energy path. So whichever the path gives the low energy, means in which path we have to consume, means we have to spend more less energy, thus that path will be preferred by the magnetic field. So like we do, so we want to struggle less to get the things, right? So similarly this magnetic field also want to spend less energy to complete its path. So similarly it can get the path here, then it will goes like this. So that we will understand better when you dealing with the reluctance and other parts of the magnetic field. So here is some terminology about the magnetic field. So main thing is that magnetic field, we are telling that magnetic field, right? So what is a magnetic field? So magnetic field is the space around the magnet under which the magnet can be influenced other object. Either it can be a magnetic material or a permanent magnet, or it can be a current carrying conductor, is called a magnetic field. And don't worry, I will give you better explanation in the next lecture. So just go with the definitions in this class itself. Okay, so what are the magnetic flux? This is the mainly the flux lines, whatever the lines of forces we have seen in the last, like these are the lines, right? These lines, so complete lines, all the lines are called magnetic flux. Okay, these are called lines of magnetic lines of forces, right? So these total number of lines are called as magnetic flux, and units for this one is Webers. So if you have the 10 to the power 8 number of magnetic lines, then it can be called as 1 Weber of flux. Okay, so whereas flux density, as density means anything per unit area, right? So similarly this is the flux per unit area is called as magnetic flux density, and units are Tesla, which is Weber per meter square. So other thing is that magnetic flux intensity, it is represented with the H. So this is basically magnetic-motive force per unit length, that is mmf per meter. Maybe we can call it as like this, per meter length. Okay, is called as magnetic field intensity. Maybe you can relate it to the term like E, electric field intensity in the electrical fields, that is volt per meter, right? So permeability, so this is a property of material to allow the magnetic flux through it. So what it permeability means, if you have any material, so whether it can allow the magnetic field or not, it depends upon what are the permeability constant it has. So it defines whether it will qualify whether it is a magnetic material or a non-magnetic material. And we all of us might have studied in school levels that there are 3 types of materials which are having the mu r greater than 1, less than 1, and equal to 1, right? So all these things we will see in the next lectures. Okay, so another thing is that reluctance. So maybe you can, by name itself, you can take it as a, maybe we can make it some intuition, like it's spelled like resistance, right? So the resistance is literally a resistance to the magnetic flux actually. So what is this? Is a property of a material that opposes the magnetic flux. There the resistance means it opposes the current flow, right? Electrons flow. And whereas this one is reluctance is opposition to the magnetic flux. Okay, so these are the main terminology of the magnetic fields. Thank you.